don't know. Thank you, Stuart, for the introduction. I'm PCC Denton. I'm a NASA postdoctoral program fellow at the Southwest Research Institute, and this talk came out of a couple different emails that I've gotten over the last year that have been people specifically asking me, can you make some of the big basis elements Saturnian satellites if you have a really large body that's moving kind of at what we would consider to be the limit of on like the very, very low end for collisional velocities. So that's something that I've been exploring, and I've been doing it using Saturn's moon Mimas as my case study because it's very fun. And we have a lot of background about a lot of work's been done recently on collisions on Mimas, so it's a good place to start. Not everybody here is as familiar with Mimas as I am, so I'm going to introduce Mimas. Here it is. There it is on the left. If you're not familiar with Mimas, you may recognize it as the moon that looks like the Death Star, and that's true. It does look like the Death Star, but it actually has a lot of other really interesting things about it as well. It is a moon of Saturn, and it is the closest of Saturn's mid-sized moons to Saturn. We call them the mid-sized moons because they're all smaller than Titan, the really big one, but larger than all of Saturn's little guys, of which it has hundreds. There's about 7 mid-sized moons. Mimas is the smallest of these. It's actually one of the smallest bodies, known to be rounded by self-gravitation. It has a radius of around 196 kilometers, which means that its diameter is less than 400, so it's actually smaller than the average diameter of Vesta. It's not very big, but despite this, oh yeah, I should say one of the things that's fun is because it's so small, if you go looking up Mimas in NASA's photojournal, you'll end up with a lot of photos like this, where it's mostly Saturn, and you're like, where's Mimas? It's right there. It's really small, and it's really close to Saturn. Despite being so small, libration data from Cassini orbited Saturn from 2004 to 2014, suggests that Mimas may potentially be an ocean world, but that's not necessarily the end of the story. So libration data is, to put it simply, Mimas's wobble as it orbits around Saturn. Mimas librates more than it ought to if it is just a fully differentiated ice rock body where the ice is just frozen to the rock event. So one of the easiest solutions to that is you can max the libration data somewhat, depending on if you have a liquid water ocean, but that's not the only possibility. The problem with this is that Mimas has no surface expression of a past or present origin. So here on the left, this is Mimas. This is the other side of Mimas. They never show you this side of Mimas. Why? Because it doesn't look like anything. But it's got a lot of really nice craters, so I wanted to show you guys. So that's the other side of Mimas, the one that Herschel isn't on. And then on the right, we have Enceladus. Enceladus is a good comparison point for Mimas because Enceladus and Mimas are right next to each other. Mimas is the closest to Saturn, then Enceladus is the next closest moon to Saturn. And it's also incredibly geologically active. So we know a lot about Enceladus, and we know that it is an ocean world because it literally has geysers coming out of the South Pole. It's the poster child for quote cryovolcanism unquote, but that's a different debate that we don't have. And when we look at Enceladus, what you'll notice is that it is incredibly geologically active. It doesn't have a lot of craters, it has some, but not very many. And the surface is covered in other types of geologic features. You have these widespread fracture networks, and then of course you have the South Polar terrain with the cryovolcanism. When we consider Mimas, it doesn't really have any of that. So it's very heavily cratered, as we can note. It's covered in craters. It doesn't have a lot of additional geology. So you go in and you map Mimas, as people have done. There's been, many of you talk to, there may or may not be some fracture networks, but there don't appear to be very many if there are any, and they're certainly not global in scale. So there's not a lot of other geology going on for Mimas. There's no cryovolcanism, unfortunately. And when we look at Mimas's craters, they appear largely unmodified. Obviously, they've been subject to mass wasting, etc. But they don't appear to have experienced extensive viscous relaxation, for example. There doesn't appear to have been any kind of burial. So on Enceladus, some of the craters look like they've been partially buried by fallback from the geysers. Not so on Mimas. So the geology of Mimas isn't consistent with that observed other ocean worlds in the solar system, like Enceladus, like Europa. But why would we think that Mimas is an ocean world at all? One, we have the libration measurements, but also there is the matter of its actual orbital positioning. It is closer to Saturn than Enceladus. And it also, its orbit has a higher eccentricity than both Europa and Enceladus, so it has about 40 times more tidal potential. basically Saturn should be squeezing the heck out of Venus, and that should do something. It doesn't appear to be doing anything. So this then leads to this conundrum where the fact that it doesn't appear to be super geologically active despite all of this tidal potential suggests that Venus should be frozen, because the easiest way for Venus to not be geologically active, if it is getting squeezed a lot by Saturn, is for it to just be frozen. So it just stays the way it is. But then how do we reconcile the libration measurements? So we have geologic evidence which suggests that Venus doesn't have an ocean. We have a lot of potential for an ocean, which is not the same thing as evidence. And then we have the libration measurements. So trying to reconcile all these things together, one thing we can do is take a closer look at Venus's cratering record and see if there's something that we can use just by looking at the craters on Venus to see if they preserve more subtle evidence of an ocean nearby. And that's something that myself and my collaborators have been doing over the last 5 years, specifically looking at the crater that makes Venus look like the Death Star, and that is Herschel. Herschel is Venus's largest impact crater. It's not close. It is very big. It's about 130 kilometers in diameter, which means the diameter of Herschel is comparable to the radius of Venus itself. Recall the radius of Venus is around 196 kilometers. So this is a very big crater. It's also a very deep crater. It's greater than 10 kilometers deep. I have asked several different people for topography measurements for Herschel, and I've gotten estimates that range from 10 to 12, depends on who you talk to. So very deep, and it's a very large, complex crater. Has a large central peak in the center. The height of that central peak is also not really published anywhere. Several kilometers is a good estimate. And in terms of its morphology, you'll note that it is, by virtue of being very deep with a large central peak, there's generally speaking no evidence that the formation of Herschel reached Venus's ice shell. We have a general understanding of what craters look like when they do reach the ice shell. There's great examples of these on Europa, and potentially some of the other Galilean satellites. This doesn't look like that, so generally speaking, we think that this formed in a thick enough ice shell to support a crater of this size. Previous to the work that we did tested the ocean hypothesis specifically for the formation of Herschel, and we began by looking at, these are all ISL2D simulations. We'll get into how we do the ISL2D simulations in a little bit. One of the first things we looked at is we used the modern estimates from the libration data, which suggests that Venus's ice shell should be around 30 kilometers thick and then have a 40-kilometer ocean underneath that. So the ice is in white here, and then the ocean is in blue, but also the ocean has a whale in it. So you know. Anyway, if the ice shell is as thin as it's supposed to be today, if Venus has an ocean, then you actually just punch through the ice shell and expose the ocean to space, which doesn't really work because then you don't form a central peak, because instead you just have ocean. You have a flat floor crater. So presumably this doesn't work. What we found is that if you instead make Venus's ice shell completely frozen, so we just take the surface temperature and establish a conductive thermal profile through the ice shell, then you have an ice shell that's actually very cold and very strong, because the surface temperatures of the Saturnian satellites are very cold. So you end up with a crater that's way too deep. We did find that you can make a Herschel-like crater, so you can produce a crater that is both deep but has a significant central peak. How you do this is you actually have a thicker ice shell and a thinner ocean. So you end up with an ice shell that is anywhere from 55 to 70 kilometers thick. At bottom case, the ocean's cut off, but I'm using an arrow with the whale so you know that he's still in there. It's fine. And this was kind of the story that we had going for a while, is that you can make Herschel, and to do it, you need an ocean, and then the ocean has to then grow between the formation of Herschel and the present day. And that's a really cool story until you do the thermal orbital modeling, and then it turns out that the formation of an ocean is not so simple. This is a plot of ice shelf thickness through time. And what it's showing is that basically the formation of an ocean generates a kind of runaway melting effect. What that means is that once the ice shell starts melting, you start forming an ocean. The ice shell starts to thin really rapidly as the ocean grows really rapidly. So then if you want to form Herschel in an ice shell that's about 55 kilometers thick, you actually have a really narrow window of opportunity. And it works out to about 100 million years in time. And anybody that does age dating or any kind of geologic theory knows that having a 1 million year window is not very good. That's a very small window, so either we guessed exactly right, and this is how Herschel formed. That would be so cool. Probably not though. Or we need to think about how to widen this parameter space a little bit. And that's one of the reasons why that motivated us going back to what if Venus is entirely frozen. So one potential solution is that Venus isn't an ocean world at all. People have been saying this, we firmly can't. Because libration models do favor the presence of an ocean on Venus. But the other reason a lot of people favor the presence of an ocean on Venus is that it would be cool. Unfortunately, we still can't fully confirm the presence of an ocean based on the information that we have from Cassini, and but with later evidence, we still can't fully confirm it. So the other option is still out there, which is that Venus, instead of having an ocean, has an ice shell that is frozen at the bed to a large non-axisymmetric core. That's what I'm showing here on the right. And when I say non-axisymmetric core, what I mean is we typically assume in our models that the core is spherical. Well, what if it wasn't? I don't know why you're laughing, it could be. What if you have an elongated core? I actually could have elongated this more so that you could tell, but basically the idea is, again, the measurement that we're trying to match is a libration measurement, so a wobble of Venus. You can wobble if you have a liquid water ocean, but if you have an elongated core, that will also give you a wobble, right? It will enhance your wobble. So that's why this is the suggestion. So one of the things that we're going to do is try to test this. But before I show you my models, there's one other thing that we have to talk about. So I'm realizing that I'm so excited that I'm talking a little fast and I sound like I'm doing a conspiracy theory, so I'm going to try to calm down. I'm just really excited about this. So the previous impact models that I showed you seem to rule out the fully frozen option, but again, we didn't completely do that because we can't confirm or deny what Venus is actually like inside. So let me talk about the other aspect of this, and that is the local impactor population in the Saturn system. So it's not so simple. Impact velocities at Venus can vary by order of magnitude, potentially. And that's due to the presence of two theoretical impactor populations that are hitting Venus to form. The first is the heliocentric impactor population. That's what we normally think about when we think of an impactor population. That at Saturn, that's going to be primarily comets. But we also have the planetocentric impactor population, which has been documented at many of the mid-sized moons, including Venus. What is the planetocentric impactor population? You may ask yourself. It could be debris that forms within the Saturn system. And I'm putting the rings up here to show you that we think that planetocentric debris would be largely ice. And that could be stuff that forms within the Saturn system, like breakup of the satellites. So there was the Jack Wisdom paper, but he's not the first or the last to suggest that you could have a moon that gets disrupted at Saturn, it becomes debris, it becomes the rings, etc. So you could break up a satellite, you could have two of Saturn's satellites crash into each other. It certainly has enough to do this, etc. Either way, you generate debris that forms within the system rather than outside of it, and thus is traveling at a different speed. For heliocentric impactors that are going to be hitting the Saturnian satellites, you can estimate their average impact speed based on distance with respect to Saturn. When we consider the speed of debris that is generated within the Saturn system, that becomes very difficult to constrain because you have to imagine how the debris gets formed to begin with and then how its speed might change over time. This is a long-winded way to say we don't know. Suggested impact speeds for planetocentric impactors that would hit one of these moons could be anywhere from 200 meters per second to 15 kilometers per second. That's a really broad range. The previous models that I showed you used 15 kilometers per second as a good planetocentric impactor speed. The reason why we did this is because it's still much slower than the heliocentric impactor speed of Venus, which is 27 kilometers per second. That's really fast. Because again, remember that Venus is also very small, 400 kilometers in diameter. If a 27 kilometer per second object hits a 400 kilometer diameter body, you could just blow it up entirely. People are worried about this. So that is the planetocentric impactor speed. the reason why it's important to try to understand what's going on if Venus gets hit by something that's traveling at 15 kilometers per second rather than 200 kilometers per second is, as we all know, there's a trade-off between impactor speed and the size of the impactor if you try to make a crater of a given size. So a slower impact requires a larger impactor, generally speaking. But when your impact speeds are now varying over an order of magnitude, a much slower planetocentric speed could drastically alter the impact process itself at Herschel, so it may change how you produce the crater, and thus it may make it easier or harder to match the morphology that we actually see. So, could a large slow impactor taken at all the way at the extreme slow end allow Herschel to form in a fully frozen Venus is the question that I'm asking. And I'm asking this so that we can get a better sense of what the cratering record might be like if you have planetocentric impactors that are traveling at these ultra low speeds that have been suggested. To do this, I use the ICL 2D shock physics code. We saw some of it yesterday. You're going to see it again today. I begin with some of the previous assumptions and I incorporate a wider range of conditions for Venus's interior, assuming that it is fully frozen. So I very impactor size the speed on that low end. And this is a scaling that has been suggested for this low end. So I test impactor diameters between 50 to 70 kilometers in diameter. I test impact velocities between 200 and 300 meters per second. That is very slow. Now, I also have consistent material conditions inside of Venus. I start by assuming that Venus is fully frozen. It has an ice shell overlying a rocky core. If you care, the rocky core is dunite, but it's really, the rocky core doesn't really do anything in these models. It's too deep relative to the ice shell thickness. And then I test an ice shell that's both fully conductive and conductive convective. Those suggested a range of convective thicknesses for the ice. So here are a couple different end members that I tested. So I have differences in the total thickness of Venus's ice shell. The reason for this is because the core could be elongated. So we do have a radius of Venus, but we don't have the radius of its core, which means the ice shell could be thicker or thinner, depending on how big the core is, and not everybody agrees on how big the core is. So the surface temperature of the ice shell is 80 Kelvin. And then beneath that, you have ice of variable thickness. And that ice also has variable thermal profiles, from a fully conductive ice shell to an ice shell that has an isothermal bottom of 10 kilometers is isothermal. This is based on modeling, thermal orbital modeling, looking at how much of the ice shell should be isothermal just from tidal heating from Saturn. And then on the right, it's possible that you can have a much larger isothermal layer, and this was based on bits to some of the gravity data. So, gotta test them all. I'm also testing variable convective temperatures, which means that basically the isothermal layer is isothermal at different temperatures because we don't know what temperature means this ice shell could be convecting if it is convecting. That is the parameter space that I'm testing. Let's go back to the question. Could a large slow impactor allow Herschel to form in a fully frozen Venus? No. Or at least not yet. I don't know. These are fresh results that I've pulled up.
I'm sorry. My hand was on my watch and decided to recite the time. It was a good time to tell you you have 11 minutes.
Thank you. I have so much to say. Okay. Anyway, I'm showing here a time series from one of the cases, and what basically the main finding is that if you have a large impactor that's traveling at such slow speeds, it's no longer hypervelocity. It's no longer it's below the speed of sound. What this actually produces in practice is you get minimal excavation, and the large slow impactor basically splats onto the surface. So you produce a crater, which is cool. You do have excavation flow, so you get a nice crater rim. But the topography within the crater actually ends up dominated by preserved material, because the impactor is traveling so slow that it effectively, and I need to think of a more scientific way to say this, it just splats. And so you have a compressed impactor that forms the crater floor. It doesn't melt. So what I'm showing here is temperature. The impactor starts off really cold and stays fully frozen. So you do have a tiny little bit of a uplift in the center of the crater here. That's just impactor material, actually. Splat effect. I'll think of a better name. Email me if you have a better name. occurs over the full range of impactor sizes, velocities, and thermal structures that I tested. So what I'm showing here is constant interior conditions, but increasing impactor speed. And what you'll notice, these don't look great. As you increase velocity over this spectrum of not hypervelocity impacts, you increase your impactor's capacity to excavate a crater. But because it's traveling so slowly, it gets better at excavating, but you don't actually induce sufficient excavation flow to produce a complex crater because you don't get the collapse and the formation of the central peak. This is because there's simply not enough impact energy to do it. With the caveat that you can do it if the convective sublayer is thick enough. And here I'm going to show a video, or I'm going to try to show a video. I know we're banned with it, but we got to see one video. So after I failed to do this many times, I took things to their extreme by using the maximum possible convective layer thickness that's been suggested. So this means that about half of Mimas's ice shell is convective. There's not really a good thermal orbital reason why this would be the case, but it's a good kind of thing. Remember, that makes the ice really weak. So if you have the thicker your convective layer, the weaker your overall ice shell is. So when this happens, you can produce a different type of crater, and it also changes what happens to the impactor, and it's a little bit fun. So that's what I'm going to show you here. So on the left, I'm plotting temperature. So blue is cold, orange is hot. So on the right, I'm plotting density, which is a good way to track what goes on with the impactor, because the impactor, again, it won't melt, it will stay cold, but it will also stay more dense than the surrounding ice. So there goes your giant impactor. It's going to excavate a crater, which is nice. So there's your transient crater. Now it's going to undergo collapse. I sped this up quite a lot, but it's a slow impactor, so you have to a little bit slowly. You have inward collapse, and so instead of having melts underlying the crater floor, you actually preserve the cold impactor buried at depth. Yeah, isn't this fun? So you do produce a complex crater in this scenario. This is not a good fit for Herschel though, because it's too big. You will note that it is about over 200 kilometers in diameter, which is bigger than Herschel, so not a good fit to Herschel, but an interesting crater that I found. I've been having such a hard time trying to actually make this work, and I just don't think it does. There may be a small window in which you can balance impactor size and velocity and the thickness of the conductive layer to produce a Herschelite crater, but it's hard to find. I said that because I can't find it, but I'm going to keep trying. Currently, no tested parameters that I've looked at through that parameter space produce a complex crater of the correct size. Here's a range of some of the ones that I tried with a more extreme convective layer thickness. So if it's cold and you do this, you just line the interior of the crater with the impactor as you normally do. And then as you increase the temperature, the impactor gets preserved at deeper and deeper depths. So there's impactor material, and you can see it slowly moves down as the ice shell gets warmer. But even for a warm ice shell, you end up preserving cold impactor material at depth for the duration of the simulation. Obviously, this would probably not last over time, but it's kind of fun to think about, because when you have an impactor that gets buried at depth, you have this concentration of this higher density zone that could produce a gravity anomaly within the basin. So here's how you get a mass-con basin at Mimas. But it's probably not going to be preserved over time, because the density contrast is not large, and it's ice within ice, so it's not really good analog. It's just kind of funny to think about. So the other thing to think about, large, slow impactors in general produce this kind of distinct crater morphology, which is most of the ones that I've shown you today, which is you end up with this massive simple crater at unusually large sizes. So you could potentially find these in the record if you were looking for them, because you would end up with these simple craters that are much, much larger than the expected simple to complex transition on these bodies. So in general, what I've been producing is likely not consistent with Herschel, even under the extreme conditions that I've been testing. But it might be identifiable elsewhere, either on Mimas or on some of the other Saturnian satellites. And I put up this picture of Penelope on Tethys because I like it, but also because Tethys is large and shallow. Penelope is large and shallow. So something to think about. The key points here are: one, A large slow impactor, generally speaking, cannot reproduce or like crater on a fully frozen humus, and that's regardless of the internal thermal structure that I use. I have even more tests that I didn't put on these slides. I have a couple backup slides that will show you even more of these, but I can't make it work right now. These results somewhat favor the presence of notional humus in the sense that I can't seem to do it. But I would say, generally speaking, what they actually favor is the formation of Herschel from faster, smaller impactor, which could better reproduce Herschel's morphology. That being said, maybe you do have these really slow guys hitting the mid-sized moons, and if you do have them, then you might be able to identify them if you find a crater that is much larger, that is large and shallow, could actually be from a large slow impactor. So something to think about. That is all I have to say. Take any questions.
All right, we have 3.5 minutes for questions. There is one in the chat by Catherine Leash, who wrote, there are
So true.
Sorry, didn't break anyone. There are very few there are very few central peaks on Titan. Perhaps that points to more planetocentric impactors, or impacts. The other option is erosion, as outlined in Niche et al. 2016, and we can chat more later. But if you'd like to pontificate on that comment.
Yeah, we should definitely chat more later.
Great pontification.
Yeah, it's just something that's troubled me since I've started studying Titan. Like, where are all the central uplifts? There's basically one, which is really strange.
This is very clearly been troubling me as well. That may be actually the case. The thing is that, I guess it depends. The impact speeds on Titan, for those who don't think about the training system, impact speeds on Titan are much lower than they are at Mimas because Titan is much farther away. So, maybe the contrast between a heliocentric and planetocentric impactor at Titan may not be as much unless
Oh yeah,
at the extreme.
it's about a factor of 3.5, I think.
Yeah, that still could potentially do it. Yeah, it's worth thinking about, and I saw that you've been working with Shigiro and others on this problem at Titan, so it'd be really interesting to compare my results to your results.
Yep, love it. Thanks, Adine.
Thank you. Yeah, Michelle, then Mike.
David also has a question.
Oh, so sorry.
Mine's probably relatively quick because I know you haven't probably been able to do it yet, but is there any thought about how fast can you get before this not forming a central peak happens, basically?
Ooh, that's a good question. I haven't tried that. So I have tried faster impactors. So I've done a lot of 15 kilometers per second because that's kind of been our standard, and I've done a lot of this. Mattia Chook suggested that maybe you can produce Herschel if you had a 1 to 2 kilometer diameter impactor traveling at 40 kilometers per second. Sorry, 4 kilometers per second. I've tested that as well, and you do kind of get this like weird intermediate thing where you no longer preserve the impactor because it's traveling fast enough that the impactor is destroyed, but you still don't produce a central peak. So I think what I can do is do kind of a survey between 15 and 200 and see if I can find that. That would be really interesting to do. So thank you.
We have 45 seconds left, so I'm gonna call on David Minton online. And maybe we'll get to Tom, probably not.
Hi. Yeah, you kind of addressed some of it. I was actually thinking about Mattia Chook's work on the sort of some young cataclysm has occurred in the Saturn system, and I'm actually wondering if the source of that was beyond Titan. Your planetocentric impactor population might actually be a higher velocity because of that, because it's coming from further away. But actually, the question I had about the modeling part is that how much of a role do things like porosity and like other things we don't really know how to constrain. You know, if Mimas is getting beaten up by stuff, it might actually have a much more porous surface.
I made this slide just in case somebody asked this question. Porosity, I've tested a couple different porosity structures. People generally suggested that the upper 10 kilometers of humus might have a 20% porosity, so that's what I'm showing here on the top. And the thing is that Herschel is large enough that if the porous layer is only 10 kilometers thick, it doesn't really change crater excavation enough to fix the issue. Or at least it hasn't for me. I'm still testing this. The problem is that doing porosity in ice is kind of difficult because there haven't been a lot of tests on it, so it's hard to be sure that that your values are correct for the epsilon alpha porosity model in ISO. As far as I know, porosity could change this, but not very much. It's not enabling the formation of a central peak where you otherwise don't get one, is I guess the short answer to your question. Good question. Sorry, Stuart, I know I've gone over time, so
Yep.
I will stop. Good question, thank you, everyone.
It's all right.